Okay, welcome everybody to this afternoon session of the 2001 INdAM Day. And it's my pleasure to introduce Professor Andrea Marchiodi. So let me give a quick introduction. Andrea Marchiodi is now full professor at the Scuola Normale Superiore in Pisa. He took his PhD in mathematics at SISSA in Trieste under the supervision of Antonio Ambrosetti, actually coming from an undergraduate degree in physics. And then after the graduate school, he spent some years at the Institute of Advanced Studies in Princeton as visitor, and later became a professor at SISSA again, first associate professor, then full professor. And then after a brief stay in Warwick, he became full professor at Scuola Normale in 2014. He got the Calciopoli Prize in 2006, and he was an invited speaker at ICM in 2014. He has worked on a variety, actually an impressive variety of problems in analysis. And I would say in the Italian community, we refer to the area more like nonlinear analysis, but perhaps a correct term is also geometric analysis. And in particular, he gave an important contribution to the Yamabe problem, conformal geometry for higher order operators, and many other problems, which it would be pointless to list because it also would be an incomplete list, I'm sure. So I think this could be enough. And Andrea will talk about, and I missed the title, I'm sorry.
Prescribing scalar curvature in conformal geometry.
Okay, thank you very much, I'm sorry.
Sure.
Because I had it on another window, of course.
Thanks for the nice introduction, and especially thanks to all the organizers for proposing me to speak. So it's really a great honor and pleasure. I was part of the scientific committee of INdAM over the past years, so this makes it even a bigger pleasure. I would like to apologize, first of all, to the organizers and the other speakers for not being able to attend the rest of the event. But this week we have actually some important exams, so I will need to leave also after my talk. Sorry, this is terrible. So let me try to share the screen. And before starting, I would like to say that most of the work I'll be talking about is joint with Martin Meyer, now at Roma La Sapienza. Okay, I hope you can see the screen I'm sharing. And
perfect.
Oops. Sorry. Okay. All right, so the problem is classical, so it became a classical problem since the 70s. I consider a compact manifold of dimension greater or equal to 3. And I consider the problem of prescribing the scalar curvature of the manifold as a given function k, defined on M, via a conformal change of the metric. Okay, so I start with a given function k, smooth, on my manifold M, and I want to deform conformally the metric so that the new scalar curvature becomes equal to this function k. Okay, so a conformal deformation of the metric means point by point of scaling a background metric G by a positive factor, which is convenient to write in this form. So this makes the equation nicer. So U is a positive function on the manifold. And the equation you need to solve, if you want to study the above problem, is the following one. Okay, so K is the given function and U is the unknown. Okay, we want to find a positive solution of this equation. Okay, so on the left-hand side, there is an operator which I will comment on. It's linear and elliptic. And on the right-hand side, there is a nonlinear term. So this is a power of U which is greater than 1. Okay, so the operator on the left-hand side is called the conformal Laplacian. And so I won't display the formula, but it transforms nicely when you change conformally the metric. And in particular, it turns out that the first eigenvalue of this operator has a sign which is conformal invariance. Okay, so the sign of the first eigenvalue doesn't depend on the conformal change of the metric here. Okay, why is it important, this spectral property of the operator? Well, let me recall that in 2 dimensions, you have the classical Gauss-Bonnet theorem. So when you integrate the Gaussian curvature, you get the topology of a given compact surface. In dimension greater or equal to 3, the situation is less rigid. And in fact, it is possible to show that every compact manifold carries a metric with a negative scalar curvature. Okay, so this was a result by Aubin, and it was even extended by Gao Yao in 3 dimensions and Lohkamp in general dimension. You can even make the Ricci tensor negative. Okay, so it is easy to deform a metric on a given manifold so that you get the scalar curvature negative. Okay, but it is difficult instead to push the scalar curvature up. Okay, so this is a very interesting and still a very active line of research. And there are fundamental results by Gromov, Lawson, and Chen and Yao. So essentially, the main tools which are used to study this problem are minimal surfaces or spin geometry. But if you restrict in dimension greater or equal to 3 to a given conformal class, so if you don't take any arbitrary deformation of the metric, but just conformal deformations, as I wrote above, then the situation is more similar to the 2-dimensional case. Okay. And in fact, Kazan and Warner proved that if the sign of the scalar curvature is constant, then it must coincide with the sign of the first eigenvalue of the conformal Laplacian. Okay, so in particular, it is impossible to reverse the sign of the scalar curvature with a conformal change of the metric. So within a conformal class of the metric, the situation is probably more similar to the 2-dimensional case. Okay, so there is a terminology depending on the sign of this first eigenvalue, which is only dependent on the conformal class. Then manifolds are said to be of negative, 0, or positive conformal class or Yamabe class. Okay, so let me list some classical results. Okay, so there is a particular case which is well known when you want to prescribe constant scalar curvature. So this is known as the Yamabe problem. And this is a problem you can always solve. So due to fundamental contributions by Yamabe, Schrödinger, Aubin, and Schoen. There is another classical case. So when you consider the round sphere, okay, and the function k is a variable function, this is known as Nirenberg's problem. And this is probably the most studied case. If the curvature is non-positive, then the problem is always solvable. And a tool which has been employed by Kazan and Warner is that of sub and super solutions, so which is a sort of a nonlinear Perron method. Okay, so therefore, I will focus from now on the positive case, okay, positive curvature, which is the most difficult. Okay, in this case, there are actually more obstructions, so not only the sign that I talked about. So if you are on the sphere, for example, so I consider the round sphere, which is embedded in one more dimension in a Euclidean space. And if U is a solution of the equation that I displayed above, then you have the following identity. Okay, so involving the solution U and the function K. So what are the quantities here? As I said, I'm embedding the sphere into a Euclidean space of one more dimension, and the xi's are just the restrictions of the coordinate functions to the sphere. Okay, so here I'm taking the scalar product of the gradient on the sphere of the function k and of these coordinates. Okay, and U is a positive solution. So let me recall that U is actually positive. Okay, so what is the consequence of this identity, the Kazan-Warner identity? Well, if you take a function k that is monotone with respect to one Euclidean direction, then you make this scalar product positive or non-negative. U is also positive, and there is no way to for this integral to vanish. Okay, so therefore, such functions that are monotone with respect to some Euclidean directions are forbidden for the above problem. So analytically, the difficulty comes from the fact that this exponent, so which appears here, is the critical Sobolev exponent for the embedding of W12 into LP. Okay, so W12 are the functions which are in L2 together with the gradient on the manifold M, and LP is a classical LP space. So this embedding is continuous but not compact. So this means that when you try to use classical tools from analysis to solve the above equation, then you have trouble coming from a lack of compactness. So typically, minimizing sequences will not converge. Okay, in a sense, so since these functions that are monotone with respect to one variable are too simple, and if the function k has more oscillations, then the chances of solving the equation improve. So let me recall some results. So there is a classical one by Moser. So this is dimension 2, but I'll mention it anyway. It's kind of similar. So if you take functions that are antipodally symmetric on S2, then you can always solve for the prescribed curvature problem. And this result was extended by Escobar and Schoen in 1986 on S3. I'll just report a simple case. So if the function k is invariant under a finite group of isometry without fixed points. So in particular, they extended to the three-dimensional case the results by Moser. And now let me mention another classical result on S3. So this is due to Barry-Coron, and there are also variants by Chang-Gursky-Yang and Schoen-Zhang under the following conditions, which might appear a little mysterious, but I will try to explain them. Okay? So first of all, here they don't assume any symmetry on the function k, but just a generic condition. Okay? So they assume k to be a Morse function, which means that all critical points are non-degenerate, so there are finitely many and non-degenerate. And they assume that at all these critical points, the Laplacian of k is non-zero. Okay, so I call this non-degeneracy assumption, and it's completely generic assumption. And then they assume the following condition. So it's in dimension 3, but I write the result for general dimension n because I want to consider it later for general dimensions. They consider this number, which might appear a little mysterious. So it's a sort of index counting condition that I will try to explain later. So you sum over all critical points of k with negative Laplacian. Okay, so just these critical points, -1 to the Morse index, so which is the instability index of the function k, and then you subtract -1 to the power n. Okay, so it turns out that if this number is non-zero, then the problem is solvable. So I will try to explain later the role of this number and why the result only holds in dimension 3. Okay, so all the trouble, analytically comes from a lack of compactness. And if I want to explain that geometrically, I need to introduce the Modius group, which is a sort of group of spherical dilations. Okay, so this is a non-compact group of conformal maps from the sphere in itself. Okay, so you can think of somehow dilations in Euclidean space composed with the stereographic projection. Okay, so they are counterparts of Euclidean dilations, but sort of brought to the sphere by the stereographic projection. So conformal maps means the following. So if you have such a Möbius map, if you pull back the spherical metric, then you obtain a multiple of the spherical metric. Okay, so again, the spherical metric multiplied by a positive factor. Okay, so these factors are called bubbles, and they have more or less the following form. So they were classified by Oban and Talenti. So they satisfy the prescribed curvature equation with k identical equal to 1 here. Okay, so which is the Yamabe equation. And qualitatively, when you lose compactness, their behavior is the following. So they try to peak at a single point A on the sphere, okay? So somehow it turns out that the volume becomes very concentrated near a single point A, and then there is a parameter lambda, which is positive and describes how much they are concentrated, okay? So roughly in, say, a local system of coordinates, you can express them in this form. So the bigger lambda becomes, the higher is this peak, the more concentrated is the volume. Okay, so there is a way to describe them all. Okay, I'm still embedding the sphere into the Euclidean space, Rn+1. And you can think of this as a sort of probability distribution, okay, of unit measure. And I can look at the center of mass of this distribution. Okay, so I can parameterize such maps by the center of mass in Rn+1. Okay, so for example, a function constantly equal to 1 on the sphere would be a solution, and then the center of mass would be exactly at the origin. But here, when the volume concentrates at the point A on the sphere, the center of mass, of course, is moving towards the boundary of the ball. Okay, so in this case, the center of mass is approaching the unit sphere. Okay, when lambda goes to infinity. Okay, so problem K, so my starting problem has a variational formulation, and solutions can be found as critical points of some energy. So I can express this energy, which I call Jk, as the ratio of some quantity involving the conformal Laplacian and basically the critical power of u at the denominator multiplied by the function k. So if you integrate by parts, so this is an elliptic operator, you can think of the Laplacian essentially, then this becomes the gradient squared with a lower order correction given by the scalar curvature. Okay, so Cn is just a dimensional constant. This is a Sobolev type quotient, but with some geometric correction here. Okay, so it turns out that when you are on the sphere, the bubble functions delta I lambda, which I considered above, are global minimizers of the Sobolev quotient. So this was proved independently by Oban and Talenti. Okay, and there are some invariances. So you can think of in Rn some invariance by translation and dilation. Okay, so this is kind of similar. So if you consider these bubble functions that depend on n+1 parameters, so basically you have n parameters from the location A and 1 parameter lambda from the scaling, so it's n+1 parameters. Well, both numerator and denominator are constant functions in these parameters. Okay? So not only they have this variational characterization, but they also appear in a phenomenon that is called bubbling. So what does it mean? When you have a solution of equations of this kind, so that blow up, so you lose upper bounds on these solutions, you can sort of rescale. So you can use somehow the approximate invariance of your problem to rescale them down, okay? So to bring this solution to maximum height 1. So they will satisfy some limit equation, and you can classify the blow-up profiles of these blowing-up solutions, okay? So Caffarelli, Guido, Sprague showed that these bubble functions are the only possible profiles. So whenever a sequence of solution blows up, then you can sort of rescale them and see the bubble functions as the limiting profiles, okay? So this phenomenon is called bubbling. Because basically all blow-up of profiles, in a sense, have a spherical profile after a proper rescaling, a spherical shape, say. Okay, so let me try to simplify things and to introduce a sort of a toy energy functional, okay? So just for simplicity, I restrict the above energy just to the Möbius maps, okay? So to the bubble functions. So I call Fk this toy functional, okay? So I'm simply restricting jk to the above conformal factors arising from the Möbius group, okay? And since the numerator is constant, okay, I just need to consider, let me show the formula again, okay? So on the bubble functions, the numerator is constant, so I basically need to consider just the denominator here in the energy, okay? And roughly, instead of dividing by the denominator, so this is cheating, but I just aim to simplify things. So instead of dividing by the whole integral, I just reverse the function k. Okay, so I'm doing this approximation, which is qualitatively valid. Okay, I'm saying that the energy restricted to Möbius maps is like integrating the function 1 over k times the bubble function to the critical power. Okay, so this is an effective energy under such an approximation. Okay, and since these bubble functions are like modifiers, so they are functions that are supported roughly in a small ball of radius 1 over lambda, I'm like integrating the function 1 over k over this small ball. Okay, sorry. Okay, so since these functions are modifiers, in the limit of lambda going to infinity, I obtain the value of the function 1 over k at the center of the ball, okay? But if I want to be more precise, I obtain also an extra term, which is has the sign of minus the Laplacian of k divided by the factor lambda squared, okay? So in a sense, I'm like probing the function 1 over k, not only at the center, but around a small ball centered at the point A. Okay, so if you Taylor expand this integral, so if you do a Taylor expansion of the function 1 over k, this is what you're going to find. Okay, so the function 1 over k in the limits, and then an extra correction term that depends on the Laplacian. Okay, so since Möbius maps are parametrized by the center of mass, which is in the unit ball in n+1 dimension, okay, and since when the bubbles are exploding, so when lambda goes to infinity, since the center of mass is approaching the boundary of the ball, so we can think of this toy function to be like an extension of the function 1 over k, which is only defined on Sn, to the interior of the ball, okay? And you can describe somehow this extension when you approach radially the boundary, okay? So we saw that when you approach radially the boundary, this toy function behaves like 1 over k, okay? And by this Taylor expansion, if the Laplacian of k is positive, it means that you are approaching it with increasing normal derivative. But when the Laplacian is negative, you are approaching it from above with decreasing normal derivative. Okay, so let me try to draw some consequences from this reasoning. Okay, so first of all, if the function k is monotone in some direction, then also the function fk is defined in the interior of the ball. Okay, so if k was monotone on the boundary of the ball, then fk is monotone in the interior of the ball, okay? And a monotone function has no critical points, so which means that, okay, you should have no extremals for the energies, okay? So basically no critical points, no solutions. So this is an indication of the obstruction given by the Kazan-Warner identity. Okay, so on the other hand, let me try to explain this index counting condition. Okay, so if the function k satisfies the above non-degeneracy condition, which was Laplacian non-zero at the critical points, well, it turns out that the gradient of this function fk, which is defined in the interior, is never zero near the boundary of the ball. And in this case, so the function, the number nk, coincides with the so-called degree of the gradient on the ball. Okay. So what is this number? this is a number that sort of counts the zeros of fk with a sign and multiplicity. Okay, so this is an example in which the degree is 0. So we just know essentially the gradient near the boundary. You can think of a vector field that points in a single direction, like in this case. So the vector field is not twisting. And in fact, you have extensions in the interior with no zeros at all. Okay, but in this case, okay, so there is a sort of twisting near the boundary. So as you go around the boundary, the vector field is sort of twisting in the opposite direction, and then the degree is non-zero. And when the degree is non-zero, there is a theorem telling you that you always have a critical point inside. Okay, so if this number is non-zero, then the toy functional has a critical point in the interior. So this is not a proof, but an indication of existence of critical points. Okay, so I try to explain the role of this sort of index condition, but I have not explained yet the role of the dimension, because the result I stated before was only valid in dimension 3. Okay, so what's special about 3 dimensions? Okay, so there is a classical strategy. So the problem is non-compact, and there is a trick to try to compactify it. Okay, so for small parameter tau positive, I consider this equation, which is a sort of compactification of the previous geometric equation. I just lower the exponent by this little tau with a minus sign, okay? And I call the equation k tau, okay? It has no geometric meaning, but now it's a sort of compact problem, and the tools of analysis allow you to find solutions, okay? So the aim, so this was a trick sort of introduced by Sachs and Uhlenbeck in the 80s for harmonic maps. The idea is to try to consider the solutions of this approximate equation and try to pass to the limits when tau goes to 0. Okay, so this sounds a bit like cheating, because of course you might expect these solutions to blow up. So for example, there are cases when your original problem is not solvable. This modified problem is solvable. So of course, in that case, these solutions must disappear. Okay, so you do expect these solutions to develop budding, so to lose uniform bounds, but hopefully not all the times. Okay, so if you give the right assumptions, then maybe you can find some solutions that do not develop blow up. Okay, so there is a fact. So consider solutions of the problem in 3 dimensions on S3, okay? Then you can show that U tau develops at most 1 bubble. So I said that solutions can lose uniform bounds, and then you can rescale them to obtain some limiting profiles. Well, in 3 dimensions, you can do this only once, okay? The idea is the following. So consider 2 points on the sphere, and let me try to use the above approximation for a sum of 2 bubbles, okay? So I just consider the energy functional on a sum of 2 bubbles for simplicity with the same scaling parameter lambda, but centered at 2 different points, A and B. So I use the rough approximation that I did before, okay? And what I'm going to find is somehow the sum of the previous Taylor expansion at the point A and at the point B. But there is also an interaction term that you can expand in the following way. Okay, so let me just report the previous formula. Okay, so what you can see is that this interaction term has a negative sign, and you can think of this as a sort of potential. Okay, so the more the 2 bubbles become close, the more this term becomes negative. So if you think physically about this, it's like generating an attractive force between the 2 bubbles centered at the point A and at the point B, okay? So they want to come close to each other so that the energy goes down. So this is true not only in terms of the location of the bubbles, but also in terms of the scales. Okay, so I could have done the same Taylor expansion, but centering the bubbles, say, at the same point A, but with two scaling parameters, lambda1 and lambda2 of different orders, okay? So if you do the same, then not only the points, not only the centers, but also the two lambdas, they want to come closer. Okay, so it turns out that in 3 dimensions, you see, this term is of order 1 over lambda, while these other terms are of order 1 over lambda squared. So lambda is large, so which means that in 3 dimensions, this term is dominating. So it means that the bubble-to-bubble interaction is stronger than the interaction of the bubbles with the function k. Okay, so if there were more bubbles, they would kind of suppress each other. So this was proved by Barry-Coron and Chang-Gursky-Yang. Okay, so in dimension 4, there can be more bubbles, actually finitely many, but not at the same point. Okay, in dimension 4, this term is still of order 1 over lambda squared, so comparable to these ones. But since you have also the distance at the denominator, if the distance becomes very small, then this term is again dominating. Okay, so in 4 dimensions, well, there can be more bubbles, but not too close. While in larger dimensions, blow-ups with diverging energy are not excluded. Okay, so this is somehow the so-called bubble towering phenomenon, and Andrea, for example, is an expert in this. And so Chen and Lin proved that there could be possibly, I mean, they cannot exclude the blow-ups of this kind. But for this specific problem, so the prescribed curvature problem, it would be interesting to find the general construction of such blow-ups, okay, when you lower the exponent a bit. Okay, so let me spend one word for the case in which the manifold does not coincide with the sphere. Okay, so when the manifold is not conformally to the round sphere, then you have an extra term in the assumption. So I show that there is a leading term, which is 1 over k. Then there is an extra term related to the Laplacian of k. But if you're not on the sphere, there is another term which comes with a factor 1 over lambda to the n minus 2. Okay, so what is this extra term? So this term is related somehow to the regular part of the Green's function of the conformal Laplacian with pole at the point A. And this is not a local quantity. So if you are expert about Green's functions, there is a function called the Robin function, which is the regular part of the Green's function. And that is hard to understand because it is not a local quantity. So while the Green's function, so the main term in the expansion of the Green's function has a sort of universal behavior, then understanding the next order terms is a very difficult problem. And in fact, so when the manifold is not conformally equivalent to the sphere, then this is always, this term is always greater or equal to 0 in positive Yamabe class with equality only for the sphere, okay? And this relies on a deep theorem, which is called the positive mass theorem by Schoen and Yau, with an alternative proved by Witten for spin manifolds, okay? So this is a term that you see only when you are not on the sphere. And you see, in dimension 3, this term is still dominating. And in fact, when your manifold is not the sphere and you are in 3 dimensions, this term is helping you to gain compactness. And in fact, Li and Zhu proved that for any manifold which is not the sphere, and for any function k positive, the problem is solvable. Okay, so on the sphere you have obstructions like for like the Kazan-Warner. But as long as you're not on the sphere, then this other term is dominating, coming from the positive mass theorem, and you can always solve for the equation. Okay, so let me continue presenting some joint work with Martin Meyer. Okay, so we saw that in dimension 3 and 4, somehow the blow-up analysis of solutions is kind of understood. Okay, and we proved the following results. So let's consider manifolds of now of dimension greater or equal to 5. And again, a function k satisfying the above generic condition, so Morse and satisfying the non-degeneracy assumption. Okay, so now I consider the approximating equation and a sequence u tau n of solutions with the uniformly bounded norm in W12 and which are converging to zero weakly. Okay, so then we prove that in this case, near each blow-up point can accumulate at most one bubble, and blow-ups occur at critical points of k with negative Laplacian. So we still see the critical points appearing in the index counting formula. Okay, so let me comment on the assumptions. So first of all, they are natural because, so why do we assume that solutions converge weakly to zero? Because if they don't, then the weak limits will be a solution of our problem and the problem will be solved. Okay, so the interesting case is when you don't have, you want to argue by contradiction in a sense. And what about this bounds that we are assuming? Well, usually solutions of this kind are found via some variational principle, which is minimization of the mountain pass theorem. And they usually do come with some energy bounds or Morse index bounds by construction. Okay. And the result is complemented by the next theorem, which somehow shows the sharpness of this result. Okay, still joint work with Martin Meyer. Okay, so let's consider a manifold of dimension greater or equal to 5 and a function k as above. Now, so the possible blow-up points are in the set, so at critical points of k with negative Laplacian. So I fix any combination of points that lie in this set, so which is a finite set. Then we can find solutions that blow up exactly at these points. Okay, so let me comment that the second theorem is false if the dimension is less or equal to 4, because I showed that in dimension 3 there can be only blow-up points. In dimension 4 there could be multiple blow-up points, but there are some restrictions. So this was proved by Yang and Li. So in dimension 4 you cannot prescribe the blow-up set. But in dimension greater or equal to 5, you can actually do it. Okay, so somehow the statement of this theorem is sharp. Okay, maybe let me skip the proof of the first theorem. Maybe I'll draw just some picture to explain the second theorem, so how we construct blowing up solutions. So let me recall the expansion of the toy function of fk. So this was just the restriction of the Euler-Lagrange functional to the set of bubble functions. So this was defined on the unit ball in n+1 dimension. So when we approached the boundary of the ball, the limit function was 1 over k, and the normal derivative had a sign depending on the Laplacian of the function k. Okay, so that was for tau equal to 0. Now you can write a toy functional also when the parameter tau is positive. Okay, and you can run a similar Taylor expansion, and what you see is that the effect of this parameter tau, when tau is positive and small, is to somehow bend this graph upward. Okay, but notice that this, in this case, when the Laplacian of k was positive, this was already a monotone graph. So if we bend it upward, it stays monotone, no critical points. But if the Laplacian is negative, then this extra term changes somehow the monotonicity of this energy. And then you're going to find a critical point for tau small and positive. Okay, so when tau goes to 0, somehow the critical point tends to become more and more peaked. Okay, so the scaling parameter lambda depends on tau and tends to plus infinity. Okay, so this is how you construct these blowing up solutions. Okay, so let me mention some applications to the prescribed curvature problem. Okay, so now we argue by contradiction and assume that the original problem has no solution. And now there is a sort of a miracle because, okay, we assume that there are no solutions of the initial problem. And then we start with this approximate equation that we can solve. Well, it turns out that for this problem, you can basically understand completely the family of blown-up solutions. Okay, so there are, I would say, few problems for which you have this nice property. Okay, so I denote by crit minus of k the candidate blow-up points. Okay, so these are the critical points of k with negative Laplacian. These are a finite set. And by the previous two theorems, all solutions of the approximate problem are blowing up. And those with uniformly bounded energy are in one-to-one correspondence with non-empty subsets of crit minus k. So basically, blow-up can occur at any prescribed subset in here. Okay, basically, we choose the blow-up points. Okay, so for any subset, which I call I, we can generate a one-to-one correspondence with solutions blowing up exactly at the set. Okay, and now we can use some tools like topological methods, min-max, or Morse theory to find contradictions to this statement, in a sense. And the reason is that from somehow some energy expansion, we know exactly the limiting energy and the limiting index, so namely the stability of these blowing up solutions. So there are formulas, but I don't display them for simplicity. Okay, so let me state our theorems. So we assume some pinching condition on the curvature. So it means that the ratio maximum over minimum is not too big. Okay, so this is our theorem. So assume to be in dimension greater or equal to 5. And let's consider an Einstein manifold with positive scalar curvature. So it could be the sphere or other manifolds, like, for example, complex projective spaces. Okay. So we still consider a function which is positive Morse and non-degenerate, so completely generic conditions. So we assume one of these two conditions. So either this pinching condition, so which is a ratio of the maximum over the minimum smaller than this dimensional constant, and we still assume the previous counting condition. Okay, so the index of the vector field that I described above. So we assume that the index is non-zero, or that the function k satisfies a stronger pinching condition. So this number is smaller than this one. Okay, so we want the function k to be pinched, but we relax this condition here. So we only assume that there are at least two critical points of k with negative Laplacian. Okay, so one will be, of course, the global maximum, and we're assuming that there is another critical point with negative Laplacian. Okay, so this condition is certainly stronger than this one, but you can show that this other one is weaker than this one. Okay. Okay, so then under one of these conditions, we can solve for the problem. Okay, let me make some comments. So for the round sphere, so we are assumed to be on Einstein manifolds. So for the round sphere, this condition is not new. Okay, so there were previous results by Chang and Yang, Ambrosetti, Garcia-Zorero, and Chen and Xu, in which so there were some kind of similar conditions. So the pinching conditions here in these two papers were actually stronger. So this was of the form, this number was replaced by something like 1 plus epsilon. Okay, so they assumed a stronger pinching condition. And this paper was assuming a similar sort of quantitative condition. But the second condition seems to be of new type. Okay, so we're not aware of any result in the literature in a similar spirit. Okay, it is sharp both in the dimension and somehow in the structure of the critical points of the function k. So if I will have time, maybe I will spend the one word about the dimension n. Okay, and the main open problem is to try to relax these pinching conditions. So in dimension 3, there was no pinching condition at all, but we need to assume that in dimension greater or equal to 5. Okay, so maybe let me try to explain why we use this Einstein condition. Okay, so first of all, I display the Euler-Lagrange energy for the modified problem. So when we insert the little parameter tau, okay, it's an energy functional similar to the one before. And we're assuming a pinching condition. So the function k, let me assume it's very close to a constant, to the constant 1, okay? So this functional becomes similar to the function where you replace the function k by the constant 1. Okay, so roughly many of the energy levels of your original functional look similar to energy levels of the functional when k is identically equal to 1. Now we use a deep theorem by Obata, Gita-Sprack, and Bido-Veron. So if you consider the perturbed Yamabe equation, so if you take the Yamabe equation and if you lower the exponent by little tau, well, that equation has some rigidity. So the only solutions are actually constant functions. So this is very special of Einstein manifolds, and it's proved via Bochner's identity. Okay, so the consequence is that, okay, you have basically an energy functional with a single critical point, okay? And the critical point is actually a constant solution. So that means that all the energy levels have a trivial topology, okay? So all the sublevels are contractible sets, okay? So let me try to draw a picture. So a typical functional, say, which is coercive and with only a critical point is like a parabola, okay? Well, we don't actually have convexity, but still we have the existence of a single critical point. So the picture when k is identically equal to 1 is that qualitatively like a parabola, okay, except for convexity. But when you introduce the function k, well, we saw that you generate critical points, okay? And the energies of these critical points tend to stratify when the function k is almost close to 1, okay? They stratify depending on the number of blow-up points that you have. So in this rough picture, I drew the family of solutions with a scene developing just one bubble. Here, the solutions developing two bubbles, and you would have more here and here, okay? All solutions stratify. Okay, so what we exploit is that somehow if you draw some lines between these stratifications, then these two sub-level sets look very similar to these ones, okay? So these two sub-levels look very similar, okay? And you can do a sort of index counting condition which relies on the Poincaré-Hopf theorem to derive then existence of other solutions that do not blow up when tau goes to 0. Okay, so maybe let me not comment on the sharpness of this result. Maybe I just spend a few words on some open problems that I find interesting. Okay. So if you want to further investigate the problem, for example, to relax the pinching condition, it might be useful to, so we use essentially Morse theory, but it might be useful to use a Morse homology, okay, so which gives you a definition of homology which is totally equivalent to the singular one. This is not just about counting critical points of a given index like in Morse theory, but also it involves the so-called connecting orbits, so which are flows, gradient flows by one critical point to another. Okay, so it might give you a better understanding of the structure of critical points. I'll go very quickly, but there are also higher order or fully nonlinear versions of the problem that I mentioned. So there is a so-called Q curvature involving like a fourth order operator instead of second order, and fully nonlinear ones involving the so-called sigma k curvature, some operation that you do on the eigenvalues of the Ricci tensor, not just taking the trace as for the scalar curvature. And you can look at the nice book by Alice Chang, published in 2004. So these quantities are nice because they are helpful to control the topology of the manifold or its Ricci curvature. But there are some difficulties arising from the lack of maximum principle or the lack of variational structure. And finally, this is very challenging. It would be nice to consider the case of complete manifolds, which is largely open, okay? And sometimes even the Yamabe problem is not solvable. So there are counterexamples by Jin. So the Yamabe problem is always solvable when a manifold is compact, but for complete manifolds, that can be false. Okay, and I stop here, and thank you for the attention.
Okay, thank you very much, Andrea. And let me see. So what happens on the... Okay, so let me start then asking if there are questions among the people here in the Zoom room.
Apparently Angela has a question.
Yes, I have a question.
Okay,
Can I
sorry,
ask?
Angela.
Okay,
Sure.
Thank you, Andrea, for your beautiful talk, very clear and interesting. I have a couple of questions. The first one is what you said about the blowing up points. So you proved that when n, the dimension, is greater or equal than 5,
yes,
all the blowing up points are isolated and simple.
but we're assuming that the energy of solutions is uniformly bounded.
Okay. Okay.
Yes.
This is in dimension greater or equal than 5. And yes. What's about the dimension 3 or 4? Maybe you said, but I didn't catch.
Yeah, so you derive that solutions have uniformly bounded energy a posteriori as a consequence of blow-up analysis. So in dimension 3 and 4, by the blow-up analysis by Yanyan Li, Changursky, Yang, it turns out that if you have any sequence of blowing up solutions, then a posteriori, their energy is bounded. And then you also show that blow-ups are so-called isolated simple. So for each point, you don't have more than one bubble forming. In dimension 3, there can be just one bubble at most. In dimension 4, there can be more bubbles, but they are separated. Okay. So this is for any sequence of solutions. But we assume we just study solutions that have uniformly bounded energy. So it's a simpler situation. In principle, they could still accumulate. You might have two bubbles accumulating near the same point, but we show that it does not happen. Okay, so we only control some families of solutions. Okay, so in fact, the advantage of not assuming, so we do assume energy bounds, and that's partially bad, I would say. If you don't assume it, you have the advantage of being able to deform the function k. And this was done in dimension 3 and 4. So if you change the function k, then you might have bounds that are uniform, and you can use somehow some deformation arguments to prove existence of solutions. That step we cannot use, and that's why we require the pinching condition. But it would be nice to show existence of those blowing up solutions developing bubble towers. because
Okay.
I think they should
Okay.
exist.
Thank
I think
you.
they should exist.
And the second question maybe.
Sorry,
Even in higher dimension, you mean, when n is greater or equal than?
In higher, yes, in dimension
Okay,
3 and 4, they are forbidden. And Chen and Lin
Sorry,
Chen and Lin had other results.
They are forbidden. Okay, this is what...
I think in dimension greater or equal to 7, they show that if there are solutions that are going up, they should sort of converge to like a Delaunay solution. So there should be a bubble towering, but somehow they should arrange them in a sort of periodic configuration. So somehow the limits of this solution should be a singular solution.
Yeah, yeah, I understand.
Or, yeah, there's still some order.
Okay, thank you. And the second question was about the sign-changing solutions. Do you think that your point of view can be applied to build a sign-changing solution, at least one sign-changing solution? Probably there are many, but...
it could be, of course, well, as you know very well, so let me try to find the right slide. Okay, just give me a second here. Okay, so I discussed that when you have two bubbles nearby with the same sign, they attract each other. But if you change the sign, if you switch the sign of one of the two, exactly, then somehow the interaction is opposite. Okay?
Exactly, there is a plus in the last term.
Yes, so it's yeah, it's a very interesting question. When you consider changing signs, say bubbling solutions, then the interaction is definitely more difficult. I don't know. So I think it's an extremely interesting question. I have no idea about the answer. So even for the Yamabe problem, it will be interesting to be able to find sign-changing solutions. Exactly. Somehow there are results in that spirit, if I remember correctly, by De Villanova and Solimini for the Brzezinski-Nirenberg problem. So somehow some phenomenon is there, but I don't think it has been studied for the Yamabe equation. I mean,
no, there are few results.
Just few results. I think some results by Amman and Humbert, but there is no systematic study. I think it would be very interesting.
Okay, thank you, Andrea. Thank you very much.
Okay. Are there other questions here in the Zoom room? Okay, if anybody in the YouTube who's listening on the YouTube channel has a question, please write it in the chat of the YouTube channel, and then I can report it. At the moment, I don't see any question. Okay, so there seems, maybe we wait a second. Okay, there seems to be no more question. So if this is the case, then let's thank again the speaker, Andrea. And okay, it's a pity we can give you a bigger hand. I mean, a loud big hand is in a live conference, but at least I can try to do my best.
Thanks.
And I don't know if you can hear it, but okay.
Thank you. I'll see you around anyway.
Okay. And
hey, thank you very much. Thanks.
Thank you very much for the conference, for the talk. Sorry. And
okay, sorry, I won't be able to attend the rest of the event, so I'm going back to my exams.
Okay, good luck. I think.
Thank you.